dialog box. All right, so we've got our part there. Okay, so what did you want to do? You want to do adjust the location of the origin? Why do you want to do that?
It's a lot easier to see on the top of the part.
Make it easier for the guy doing the setup, right? And so what's the procedure to move the origin? How can we move the origin?
Highlight the whole solid body. Say translate or go to copy. Translate.
So I can select the solid.
Right click.
Copy. Translate.
When you move instead of
I want to move it. And I want to move it 0, 0. What's this?
-1.5.
That works. What information do we have to know in order to do that? We had to know the distance of the top surface that we wanted to be at the origin from the origin. In this case, ended up being the thickness of the part of the height. How else can we move the origin?
I think you do edit and then move origin.
Edit. Move origin point. And now what? Yeah, move it to some random point in space.
Just to smash it first to get all the edges and points identified first.
If I make geometry by smashing it, we don't want to make surfaces, we do want to make a wireframe. Now I could edit move origin point, and I can put it the midpoint of one of these lines. I can put it at the midpoint of one of the features. What if I wanted it to be the midpoint of the block? Well, what if I want to use move origin to do it? I can go draw a line between 2 points. In the center of that line now you click on the right spot. So assuming that it's a rectangle and not a parallelogram, that's the center of the block, right? That's what the rectangle is, a parallelogram. It's a special case. And you had one other way to do this, right? Line based.
Yeah.
And so let's say we actually wanted it to be on the bottom. When might I want the origin to be on the bottom?
Top of rough.
If we're going to do a facing operation on the top of the workpiece and we care what the thickness of the finished part is, we want the origin to be on the bottom. Right? So if I say I want the origin to be on the bottom, I can say edit orient part align Z. I'm going to select the face first. Sub elements on, highlight on, select the face, and edit orient part align Z. And apparently I selected the wrong face, but that'll also put it in the center of that face. All right, so there's 3 ways that we noted that we could adjust the origin of the workpiece. You can do all 3 of those methods using the automated interface that you're going to use through the project. You'll have to decide which one you're going to use. Okay? So there's not one that's more right than another. But you'll want to move the origin to the top of the workpiece after the file comes in. And you'll want your program to be adaptable enough that if the file has a different thickness, it would still work. As we go through and do this. Okay, so what's the next thing we have to do? We've got our origin figured out. We've got our tools defined. We've got our P-tops created. What's the next thing we have to do?
Create operations.
We have to create cutting operations, right? And so the first one is to create a spot drilling operation. And that one's easy. It acts on that whole 6 that we created, the one that connects all of them. Then what's the next operation?
I would say drilling all of one of the same size holes.
Okay. So then you're going to have, so how did we create our tools again? First we had to figure out what the dimensions of the holes were, right? Then we selected tools. Now we're going to have to create operations, and the operation is going to have to select the correct tool to do that operation. Right? What's the next step? We want to automate our code creation. We created our cutting operations based on the tools that we selected and the P-top features. I like simulate. Although in a fully automated system, we might skip the simulate step. I'm not sure. No, I think I would simulate it. Because if you simulate it with collision detection turned on, it will throw an error if it crashed, right? I think we should simulate it. Thank you. Just say it doesn't crash. All right, simulated. Okay. What's next? So we already picked the machine, right? Because we told you incoming which machine you were allowed to use.
We define our coordinate system we're going to use, like our G54 or whatever.
We have to decide what works. Right? So if we don't decide what coordinate system we're going to use, how will it be picked?
False.
If you use the post processor that we created here at WPI, it defaults to G54, and it says that it defaults to G54 because you didn't tell it which one it was. So this is the part that you're going to have to practice on as you go through the operations here and to create your program so that it could make this part. With knowing that when we test the program, we'll use a slightly different part. So if all of your program does is make code to cut this part without recognizing features from the part, then it's not going to work. So how are you going to learn how to automate the process? So we know how to do it manually. You can all sit down with the software, with the saw model, and a tool list, and you can manually program this hardware, right? How are we going to get the right feeds and speeds? Database lookup. Just like our tools, database lookup. So those tools also have feed and speed data associated with them. So if you use that, you will select feed and speed for it. So how are you going to learn how to do the automation part? How are you going to learn to do the automation part? I mean, that's a method. So if you go up here, help, this free API and macro help. This is where we want you to start as you work on the assignment. As you go in here, you can learn about what's new. But since you don't know much about what's old, I would skip the what's new part. If you've been programming free macro since 2011 or so, you might really care what's new with the help because they reorganized the help file since then. But none of you guys remember what the help file looked like before, do you? Perfect. All right, so what we're going to have you do as you get started this week working on this is go to the API Launchpad, and they developed this series of exercises to train people how to use this process to go through and automate these. And so what you're going to want to do, either as a group or as individuals, and then compare notes. I don't care how you organize that within your group. But don't have it be one person learns all of this. So the whole group needs to learn it, regardless of how you do it. we're going to go through the Launchpad exercises, and it steps you through so you can learn about pursuits of APIs. I don't know if I would have picked all the same numbers, but it steps you through how to identify features on a workpiece, how to choose tools based on a feature that you've identified, and it goes through the process for creating macros and learning how to do this. They've got sample files as you go through this API programming tutorials. You can use their sample files, or you can read the tutorial and try to enact it on your file without going through their files first, right? So you don't have to use it as a click-by-click. You can read the click-by-click instructions and apply them to your part as you go through. So this will step you through that. We were going to have this be due this week 7 is the last full week, and then there's like 2 days on that following week. So we'll have it be due on the Friday of week 7. So you've got now almost 4 full weeks to work on this. People that have gone through and done this and solved this problem have said that it can take up to 40 hours to figure it out. I don't know if that was a person that had a lot of experience programming or no experience programming. I believe it was somebody with very limited experience programming. If you've been programming in some Microsoft, so Visual Studio kind of products for a long time and you're really good at that, it'll probably shorten that amount of time. If you've never done any programming like this before, then it may lengthen that amount of time. So I highly recommend, although we're not going to be tracking this, that you put some serious effort in this week to at least figuring out how long you think it's going to take you to do this project. And as we go through for the next 4 weeks, what I'll do is I'll have each of the groups present a progress report. So the progress that you've had up till now for the whole class to review. So we'll figure out a schedule where you guys can present. You guys want to use Thursdays or Mondays for that? So I have a lot of time. Thursdays is better for that? Okay. So starting next week, not this Thursday, but starting next week, I'll have a schedule where some of you will present the progress that you got. We'll make sure that everybody presents throughout the week. You guys should be here for that presentation so that it's interactive. So that, for example, when Brian says, I really can't figure out how to make VCOMs, then Kyle can say, oh, that's easy. All you got to do is this, right? So I want to have the class work together on this project to get it going. I had those cards. I carried them around in my pocket for like 3 days, thinking that I was going to need to take them out and talk about the things you guys wanted to learn about from Thursday morning. And they're not in my pocket right now. I know it was sitting. It was sitting on my dresser at home, waiting for me to stick in my pocket and carry them around today. But so we talked about tool life stuff at the end of class last week, right? What was something else that somebody wrote on a card on Thursday last week that we want to learn more about in this class? Anybody want to volunteer? What's something somebody wants to learn more about in this class?
I remember writing.
Because I talked about all the stuff I want to talk about today. Now we have some free time where we can talk about things you want to learn about instead of stuff I want to teach about.
I remember writing pros and cons of 5-axis.
Like so pros and cons of 5-axis versus 3-axis machining?
Yeah.
Okay. So you guys have all done the 5-axis lab now. So why would you want to use a 3-axis operation to make that part? So you're making that pyramid-shaped part. Why use a 3-axis operation? The surface finish looks better on the 3-axis part. I was going to use the whiteboard, but all I have is Sharpies. So usually not clear. It makes it sort of single use. What controls the surface finish on a part that was made like that with a 3-axis? Go ahead.
The radius of the tool used to cut it.
The radius of the ball,
Yeah.
the cutting radius, yep,
Distance between steps.
and the distance that you step down. And so if we look at a cross section of that part, that's the shape we wanted it to be, right? And the actual shape was like this. And so if you want those little bumps to be smaller, then you change either a bigger radius, right? Or a smaller step down. And so and there's a limit to how big the bigger radius is going to help, right? You can just have be more spread out if they're not. So the thing that really makes a smoother surface there is smaller increments on the step down. What does that do?
Makes it take longer.
So surface roughness is proportional to time. It is a very direct relationship, and to get a finer surface roughness, you have a lot more time. Okay, now you said that when you did this operation, it was a smoother surface than when you did the 5-axis operation. I saw at least one person make a funny face. Was there anybody that didn't get a smoother surface when they did the? So was the cut time longer or shorter for the 5-axis when you did it?
The 5-axis was longer.
The 5-axis cut time was longer.
Well,
The time where the tool was engaged with the workpiece material, was it longer or shorter? Setup was longer. Absolutely, setup was longer. Your time interacting with the machine tool was longer because you had to, for one thing, you were learning how to interact with the machine tool. So setup definitely longer on the 5-axis program as you get it. But the time that the tool was actively engaged with the removing material, was that longer or shorter? Much shorter on the 5-axis part. But you noted that you got a better surface with the 5-axis part back here.
3 different services.
You got 3 different surfaces with the 5-axis part, because you did 3 different kinds of cutting operations on the 5-axis part, right? And so, I mean, the whole function of that series of labs, those 2 labs together, is to sort of get us thinking about the difference in these different operations. So, I think I know why your surface roughness was worse on the 5-axis part than it was on the 3-axis part. Did anybody else experience that they had better surface roughness on the 3-axis cut? What's going to impact the surface finish primarily on that 5-axis part? Go ahead.
Is there a tolerance we had to adjust at some point?
So there's a tolerance setting in the software, and so you may have had the tolerance set to a bigger number, which allows it to calculate the tool path faster, but then it doesn't control the tool as precisely. So that could be it. So it could be the tolerance setting. What else is going to, if the tolerance setting is the same between the 2 programs and one's got a better roughness than the other, what's going to impact that?
The part of the tool is
So,
fitting on the side of the
right. So the amount of tool, the tool overhangs, the amount of tool that's hanging out of the collet that we added in will impact the deflection of the tool, right? Also, the amount of workpiece overhang, so the amount of workpiece that's sticking out of the collet that it's held in, will impact the deflection of the workpiece. If you get those tuned just right, so the deflection changes orientation depending on the rotation of the tool, right? So if you get those timed just right, you can set up a resonance, and you get that thing humming. It sings, it makes noise, and then you'll get what's called chatter on the surface. And so my guess originally, because I didn't think about the tolerance, was that it was the length that you had of either the workpiece or the tool that set up some resonance that was getting chatter. So that could be it. In general, though, we expect to get a smoother surface when we've got the side of the end mill engaged with the workpiece, which you had one cut there. the side of the tool is engaged with the workpiece. You had to cut where the bottom of the tool is engaged with the workpiece. And so you get a different surface finish, right? So you get swirly marks when it's the bottom of the tool engaged in the workpiece. You get more striations when it's the side of the tool. Striations with sort of diagonal scratches on them when you do that. And you get these very regular scallops when it's the radius of the tool stepping down. And so decide 5-axis, 3-axis, which one's going to be better for your operation? What are the things that you're primarily going to consider? Whether there's a 5-axis machine available, right? So that's step one in our automatic tool selection, or automatic operation selection. So if you have a 5-axis machine available, so let's say you either have one available or you're purchasing a machine for this operation, right? So you're specifying a machine for the operation.
How many parts are you doing?
Yeah, so if you're going to make 3 parts ever, then you're probably not going to invest in a machine that costs more. The 5-axis machine typically costs more than a 3-axis machine. So how many parts you're making total, and what the throughput is, what the takt time is that you need those parts to be coming out. And so if you need them to come out faster, you might need the 5-axis operation. So once you set it up once, the second part you just drop in the fixture and press go, right? So it's that the initial setup takes a little bit longer. The second one you just drop it in the fixture and it goes. So we'll consider the throughput that you need, the total number of parts that we're making, and anything else we want to consider?
I mean, if you can't make it with the 3-axis.
If you can't make it with the 3-axis, then it's a 5-axis part. That's easy. It's when you can make it either way, right? I mean, I know people that just spent $250,000 on a 5-axis machine tool when I guarantee they're only going to use it to do 4th-axis positioning and then 2-axis operations. But they have other reasons where they need that particular machine. But the thing that they're buying it for needs a rotary. It's cheaper to buy the 5th-axis setup than it was to buy one that's 4th-axis. They came pre-configured that way. But you're gonna consider these things. These machines can range anywhere from $30,000 to $1 million. Anything else that make it better?
What?
You're the one that has the question about deciding between 3rd and 5th-axis machine. What else? What else?
The 3-axis is easier to program, so it might be easier to automate.
3-axis, is it easier to program? It's easier to set up. I'm not certain. I think you have the impression that it's easier to program because you've done it more. I'm not certain that if you're versatile at doing both of them, I'm not certain that one. What else do you want to look at? Either a 3-axis lab or a 5-axis lab. On Thursday this week, we're going to talk about factory automation as opposed to software automation. So we spent the last 2 days talking about how we're going to automate the software. I'm going to throw that at you, and you guys need to work on it. Come back with questions so that we can go through that. If there's something we need to figure out, be ready to do questions and answers on that pretty much for all the days up until that's due now. But on Thursday this week and Monday next week, the week after we don't have a Monday? We have Monday next week. So if I say that it's going to be on a day that don't have class, we really don't have class that day. I just don't remember what day it is now. So Thursday this week, Monday next week, we're going to talk about factory automation and how you actually figure out the process of, are we gonna put a robot in this? Are we going to, how are we gonna interact the two machine tools with each other so that they're passing the part from one to the other, and those processes. They will talk specifically on Thursday this week about programmable logic controllers. And so she had dinner a couple times with the guy who invented the programmable logic controller. And so he tells the story of how he invented this. And his job was he was a controls engineer back in the 1960s, setting up factory control systems. And so you guys, who's used a relay for something before? So could you explain, Brian, what a relay is and how it works?
So it's basically very, I don't want to say large, you can deal with one type of current instead of having a manual switch, it's an electronic.
So it's an electronic switch. So you can pass a current through it and turn that on and off by giving it a signal that says whether it should be on or off. And so factory automation systems in the 1950s and 60s and into the 70s were all controlled by relays. Because there were relays all over the place that said when this is going to turn on, when this is going to turn off. A bottle would go past the light sensor or some sort of sensor, a touch sensor, and it would turn a relay on or turn a relay off. And the logic that goes behind that now is embedded in how you ran the wires. So all of the logic of one of these factory control systems is in the wiring diagram. And you connect this relay to this relay, and hundreds of miles of wire running around cabinets connecting relays to each other in order to control this. So 1969, New Year's morning, this guy Dick Morley, he woke up hungover, thinking, well, I don't have to go to work today, but I do have to go to work tomorrow. And those hundreds of miles of wire and relays, it's really kind of a pain in the ass. There's got to be a better way to do this. So sitting at his kitchen table, a little bit hungover, he figured out that transistors are like switches, which makes them like relays. And you can put a whole boatload of them in a really small package. And so he figured out that he could invent a programmable logic controller and now have one little box that basically was doing the job of hundreds or even thousands of relays spread out around the factory. And that's what created him a $10 million industry that he was following up. So we're going to talk about programmable logic controllers. We're going to talk about how you program them and the thoughts that goes into that in lab next week. I want you to still work on your this pre-automation lab, but next week we're going to do a lab exercise where you actually get to run some virtual PLCs, go through some programming exercises, and make some things happen. So that's what I got for today. I'd like to thank you all for your attention, and I'd like to thank so many of you for showing up today. Mondays is better than Thursdays, huh?